Hi, my name is Aashish. Today, I'll be presenting our paper towards realistic generative 3D face models. It's a joint work between Carnegie Mellon University and Meta. Photorealistic 3D face generation has sparked a lot of interest in the domain of computer graphics and computer vision, fueled by applications such as creating virtual avatars, face animation, expression transfer, and downstream tasks in computer vision such as 3D face reconstruction. Generally speaking, there are two approaches to generate 3D faces: computer graphics and machine learning algorithms. They both have their own set of pros and cons. Computer graphics based algorithms can provide easy control over expressions, lighting, skin texture, camera position, etc. They are also more realistic. However, they require a significant amount of artistic expertise, which can be both time consuming and costly. On the other hand, machine learning algorithms can synthesize face models with natural image statistics, useful for many applications. However, they require a huge amount of data and fails to capture subtle expressions, high frequency details, skin tone, and illumination. There are a few existing methods in this direction that tries to reconstruct and synthesize 3D faces. Firstly, we have 3D based explicit models that generate smooth mesh and linear texture of low resolution, so when rendered it doesn't look quite realistic. Then there are implicit models, for example neural radiance fields, that can capture high frequency details, but such representations can't be used in graphic engine pipelines, and most of them require multi-view images and they are not very time efficient. In this project, we leverage StyleGAN to generate high quality texture and a detailed mesh in single run, which can be directly consumed by graphic engine pipelines. Here I present our pipeline, which is self-supervised 3D face synthesis and reconstruction. So given a random noise Z or W of StyleGAN's latent space, we can generate a 2D image from a StyleGAN generator. Now our shape module transfers this 2D image into a mesh which is detailed, which captures high frequency details, for example wrinkles. Then we have AlbedoGAN, which can predict albedo directly from StyleGAN's latent space for the same corresponding identity. Then we use differentiable renderer, which takes mesh, texture or albedo along with pose and lighting information to generate a rendered image. The loss between iRender and iStyleGAN is applied to train the AlbedoGAN and shape module. Here I explain the AlbedoGAN. So given a random noise, we can generate StyleGAN's image, iStyleGAN, and then we perform 3D projection to get the unwrapped texture. Now we flip this image and perform 3D projection again to complete the missing information in the obtained texture. Then we use spherical harmonics to capture the illumination map, and this is how we extract albedo and shading map or illumination map from the texture. Now this albedo is used as a ground truth to train the AlbedoGAN, which is basically a StyleGAN based generator. We have applied identity loss to maintain the identity similarity between generated albedo and the corresponding 2D image. Here are some of the results of AlbedoGAN. So as you can see, our AlbedoGAN can generate high quality and high resolution images of 1024 x 1024. Here's the shape module. So given a 2D image, we first encode the image into a higher dimensional embedding, from where we predict shape, expression, pose, and lighting parameters. The shape, expression, pose, and lighting and pose parameters are given to flame model, which gives us a coarse mesh, which doesn't have details. Now to capture details, we use StyleGAN's latent code, C or W. We have a displacement generator, which gives us per vertex displacements. Now we fuse them together to get a detailed mesh. Here are some of the results generated from our pipeline. As you can see, we can generate quite realistic high resolution images. Here's a video. So as you can see, we can perform quite good reconstruction. So given the 2D images, the left hand side images, we can perform reconstruction which are like quite close to the original images. So our identity similarity loss is very low. We have also compared our method with the state-of-the-art reconstruction benchmarks, the Now benchmark and the Really 3D benchmark. And as you can see, our method, despite being an unsupervised method, is able to perform at par with these methods like Deep 3D, Deca, and Mica. On the Now benchmark, it lies on the third spot, just below HRN and Deep 3D. The HRN and the Deep 3D are supervised methods. However, our method, being unsupervised, is able to perform at par with the state-of-the-art. So in the future, this research can be expanded in many directions. So one of the thing is like leveraging 2D assets to build 3D models using hybrid representations that can be used in graphic engine pipelines is one of the good directions, because explicit representations like meshes are morphable and can provide easy control over different features. They are easy to integrate with graphic engine pipelines, but they are not able to capture high frequency details, for example hair or eyeglasses. However, implicit representations have the capability to capture these details, for example hair, eyeglasses, clothing. But they are not easy to control and they are not very efficient. So one of the directions where this research can be headed is to combine these two approaches and come up with a hybrid pipeline leveraging the benefits of both implicit and explicit models. So yeah, thank you so much for listening to my presentation. Thanks again for listening me. For more details about the project, you can check out our project page.